So I'm very happy to be here sharing with you this discretization technique that we affectionately call HPS, hierarchical Poincare-Stackhoff method. I feel like the other talks are like the introduction to my talk. So what you're going to see here is a high order discretization technique that comes with an efficient direct solver. In the case of low frequency Helmholtz problems, you can get linear scaling as you can with nested dissection. But when you go to high frequency problems, scales into the 3/2. The important thing for high frequency is that the constant is small and I'm getting high accuracy. The camera guy. So this is joint work with a collection of people, and you'll see their names appear where appropriate. This is going to be our poster child for this talk, is just the Helmholtz problem with a smooth coefficient here. And our geometry is a square, and it's Dirichlet boundary data. And the idea with the method, or our goal with this, creating this method, as I said before, is to create a higher order discretization technique so that we can get high order accuracy. We want the scaling to be into the 3/2 when we're in high frequency, so we use dense linear algebra there. And then to accelerate it using hierarchical or fast algorithms in fast linear algebra when we're in low frequency, and then have a very small constant for both the pre-computation and the solve. And that small constant should go both ways for the fast and the dense linear algebra version. And the intuition for the algorithm is very simple. So it starts out just like a typical nested dissection algorithms, partition the geometry into a collection of small boxes, discretize each of those boxes to high accuracy using a spectral discretization. Then we're going to glue them together, and that's where the novelty here is, that we actually glue them together using Poincare-Stackhoff operators, and this allows us to achieve the high accuracy and not to see pollution. So we move to the high frequency regime. So if you just glue them together naively, you could end up with a not so fast solver, but if you follow the inspiration of nested dissection, you get your nice scaling algorithm. And so given the hour, we're doing cartoons, and you get more out of that anyway than if I had to put a bunch of math on the screen. So first, I'm going to present it talking about the Poincare-Stackhoff operator, the Dirichlet-Neumann operator. That's the one everybody's most familiar with. So this is the operator that takes in Dirichlet data and spews out Neumann data. So he's a nice little linear operator that we're going to construct. And that's what we're going to build to glue our little boxes together. So this is a cartoon of the algorithm. And so we start with the pre-computation. So you're going to get a direct solver at the end of the day. And what's really nice is that you pre-compute this. It has a little bit bigger constant, but you do it once, and then the solves are really cheap. So here we've partitioned the geometry into small boxes. So there's 16 boxes here, and there's going to be 2 levels into my binary, or in my quad tree. And then on each of those boxes, I discretize with the higher order spectral method. So here is just a tensor product Chebyshev method on each of the Chebyshev discretization on each of those boxes. And we're going to construct approximations to the Dirichlet-Neumann operator and a solution operator for both of these boxes. So the Dirichlet-Neumann operator is what I had described before. It's just an approximation. And then here, the solution operator takes the solution on the boundary of this box and gives you the solution on the interior. Now notice I don't have that. I only have solution on the outside of the entire box. So I need to come up with a way of creating the boundary data for these leaf boxes. And to do that, I'm going to build my hierarchical solver. So I have a way to propagate boundary data. So now we're here. And what we're going to do is we're going to eliminate these interior edges here in blue. And in doing that, we're going to construct a Dirichlet-Neumann operator that lives on the boundary of this box, and a solution operator that takes the solution on the boundary of this box and gives me the solution there. So, and then I can toss the Dirichlet-Neumann operators for the leaf. They're gone. And so we can keep doing this. I have these vertical edges. I'm going to eliminate them in the same manner. And I'm going to make it up the tree until I end up at the top. So how do we do this merge procedure? It's just saying that the flux and the solution are continuous through this edge. And it's 2x2 block linear algebra. You guys can go home and have fun. Or you can read the paper. So now this is the pre-computation. That's it, you're done. And then the solve is simply taking the solution on the boundary and applying that solution operator so you get the solution here. Small matrix vector multiply, keep going, have fun. You end up at the leaves. You have the solution everywhere. So what's really nice about this method is, complexity. So the dense linear algebra version is, so the cost of the algorithm is dominated by the merge procedure in the dense linear algebra case. And so you invert a matrix that's on the order of the number of points on that shared edge, the interface. So if you have n squared points in your square, then you're inverting a matrix that's square root of n in size, dense linear algebra, into the 3/2. So that's where that number comes from. If you want to apply the Dirichlet-Neumann operator on the top for the geometry, that's linear cost, because that's square root of n squared elements in that matrix. And then n log n to go down the tree to do your solve. And the constant associated with this is really cheap. You'll see that shortly. All of this can be changed, but in the case of low frequency, but I'm not going to focus on that so that we can get to some of the fun new stuff I've been doing. So just so that you can see that we're actually getting high accuracy for this discretization technique, we consider 4 problems. We have a Laplace problem, a Helmholtz problem, 12 wavelengths in size, 100 wavelengths in size, and then maintaining 12 points per wavelength. And then these are different accuracies that the linear version of the solver is set at. But if you want, pretend we're here, and then we're in the land of almost, we're in single precision accuracy. So if I asked for 12 digits, I get 10 for Laplace. And you see that low frequency Helmholtz and even high frequency Helmholtz, I'm getting that accuracy with 7 million unknowns. But at 12 points per wavelength, I only get 7 digits of accuracy only. Okay, some of you think that's cute, but I said that I was going to solve variable media problems, and I promise we're going to see some. So now we're going to look at free space scattering problem. So here I'm sending in an incident wave to the variable media, and we're recovering the scattered field. And so that's characterized by this free space Helmholtz problem, where here's the total field. So here's the incident field, and you add the scattered field. The scattered field is our unknown. And we've built a solver for smooth B, large high frequencies, and multiple right-hand sides. And so these were run on a modest desktop computer written in MATLAB, so there's no parallelism. And then there's a little caveat that I used impedance to impedance operators and not Dirichlet-Neumann operators, but it's more fun with the linear algebra. So here is the first experiment I'll show you solutions to with variable media. This is the function b, and this is the plot of the total field. And we're recovering that to 9 digits of accuracy. So here n is the number of discretization points, points per wavelength, the convergence error, and then the time for the pre-computation, the time for computing the field in the exterior of the box, and then the time for computing the solution in the interior. So at 20 points per wavelength, I get 9 digits of accuracy with 6 minutes on a modest implementation of MATLAB, and it takes me 3 seconds to solve. And, oh, I'm so close on time. I'm only going to show you one movie from this. I'll show you this one because it's more fun. So this is 100 wavelengths in size, this problem. So the more fun movie that really illustrates the robustness of the algorithm is this, we call it the bathroom glass. It simulates dielectric gas, and it's 80 wavelengths across. And this is a plot of the total field, but you'll see that in a second. So if you have epilepsy, please don't look. I'm not being funny. This has been a problem. Okay. So what you're looking at here is the real part of the total field as we send an incident wave into that geometry or that media. And you can see that the waves are bouncing quite a bit. This is 1,000 solves. It took an hour on the computer. And you can see that the fact that we're getting 9 digits of accuracy on this problem where the waves are bouncing in such fashion is, it's just illustrates the robustness of the algorithm. So we can do, from here, we can do inverse scattering. So that's when you send, okay, audience. You guys know what inverse scattering is. So our goal is you sent in an incident wave, you've recovered your scattered wave, and your goal now is to recover the B function, right? And our procedure for doing this is something called recursive linearization. So this is a much nicer problem than the problem that seismic imaging is, right? Because I can actually get information from everywhere, but it illustrates the potential of the algorithm in the inverse scattering setting. And the recursive linearization process essentially says, oh, let me go back. We're going to approximate the solution with a series. This is our basis, and the basis corresponds to one frequency. And we're going to approximate the solution, the coefficient here. So this is essentially the Born approximation, but how we create this approximation is what is the recursive linearization process. And so essentially the big key there is initializing with the lower frequency guess or solution. So we did brain or chat? We go brain. There was no vote. So this is a recovery up to 5 digits of accuracy of this media. We call them brain function. And you can see this is the updates to the approximation of the media as we sweep through the frequency regime. So this is over 1 million PD solves, ran on a server, still a MATLAB implementation, and it took 2 days. Oh, this one doesn't have that. So now we get to the new stuff, which is the adaptive version of the algorithm. And because some of you have seen this before, so I want you to know that I'm doing things. So the adaptive version of the algorithm starts out pretty straightforward, right? If I'm solving a variable coefficient problem, I first need to make sure I'm representing the solution or the coefficients correctly in the basis or accurately. So that's just, I call that the interpolation step. And so here we have 208 leaf boxes. You'll get to see the experiment this corresponds to in a minute. And then what we do is we go through and we have some type of error indicator, and we're going to pick which leaf boxes we need to refine. And then we update the solver, and then we compute another error estimate and sweep until we get our error estimate down to what we want. So the question is, how do we actually compute this error estimate? And this is where we get to exploit our choice of basis. So we are using a Chebyshev basis, which essentially means we're doing a Chebyshev approximation. So we're going to look at the Chebyshev coefficients in each direction. And we compute this guy who tells us essentially what the decay of the coefficients is like for our basis. And we look at the maximum of those values. And then we set some indicator S_div to be the max of those divided by 4. And then any box that has this coefficient or, I don't know, indicator bigger than that threshold gets compressed or gets refined, and then you proceed. So what's nice here is because we have this fast solver that naturally partitions the geometry, updating the solver is cheap. So this wouldn't be efficient if I had to re-invert the entire matrix every time, right? But because I'm naturally doing chunks, this is inexpensive. Okay, so to see them in action, first we'll do some elliptic problems. This is a boundary layer problem, and the boundary layer is determined by the size of alpha. So alpha small equals tiny boundary layer. So here it's 10 to the negative 3. So that's 10 to the negative 3 is size, and this is the mesh. And you can see 65,000 boxes versus 2,000 is pretty nice. And we're getting a high accuracy solution. And then so this is I call it an oscillatory problem, but still an elliptic problem. And our solution is given by this, and we set a stopping parameter 10 to the minus 6. So you can see as we go into the corner, the oscillations increase. And if you used uniform refinement, it'd be a lot. This is estimated, right? I don't have that kind of time. But we only need 1,000 or 1,300 boxes. So leaf box. So now some problems that you might be more interested in. How does this work? So those were elliptic. How does this work for Helmholtz problems? So here I'm going to have a smoothly graded change in the velocity profile. And the solution is not known here, so we compute an approximate solution using uniform refinement. So this is a plot of the velocity field, and we have a source term here. It's right here. This is the plot of the adaptive mesh. And you can see that it's picking out the change in the wave speed. And we're getting the accuracy that we're asking for, and it only requires 800 boxes. Then as you increase the frequency, as you expect, you need more discretization points. It's still finding the change in wave speed, but it's also finding places where the waves are changing direction in the top because of the reflection. So this has a perfect reflecting boundary condition of 0. So all sorts of fun bouncing going on. And then once you get up to a higher frequency problem, essentially it's not worth doing adaptive, but that we kind of expected. So that's not a big deal. So essentially what I've shown you is a higher order discretization technique that comes with a really nice, efficient direct solver. All the timings I've reported are very modest, I think, in terms of what we should expect computationally from it. Once we move out of MATLAB and then into the HPC environment, this is going to be fast. We naturally decompose the geometry, and it's in a very classic way. So we'll get to exploit a lot of the already developed techniques for doing that. So we're going to continue. My goal is to keep pushing it towards applications and developing the tools that we need to do that. So that includes things like HP additivity, complex geometry, so moving away from squares. For those of you that want to mesh other things, we can do that. So with that, I'm going to leave it and hope that the last talk wasn't too intense for you.
We have a few seconds for question.
Reed?
Directions, it says HP additivity. Have you gotten anywhere in the, so I guess what you just showed us was H?
Yes.
Did you get anywhere with P yet?
No, I haven't played with P yet. So I have an idea of how to do this, right? So if we have a sharp interface, we see first order convergence, but that's something that we can naturally detect. So with the indicator. So then we would just reduce the order, the discretization where we don't need the higher order.
And what about the Helmholtz discretization? Is still finite difference, or any plan to move to different approximation like DGs or whatever?
It's not finite differences. So it's a spectral collocation.
Yes.
So at the moment, no. I don't think moving to DG is going to help in high-frequency Helmholtz. So
That could be useful for seismic application.
we'll talk offline.
Okay. Any more questions?
Would this approach be applicable to boundary elements, spectral elements, and in the case of a homogeneous medium?
So in homogeneous, I would, okay, make a lot of enemies in there. In the case of homogeneous, I would tell you to use a Green's function and have fun. Yeah. So I do work on integral equation solvers as well. So this, in terms of using a volume integral for these types of problems, they have yet to develop anything that will beat this in terms of accuracy and speed. So, in fact, I'm converting people. So the work with Leslie Gringard and Carlos Borgs, they had built their own solver and it was too slow. They approached me to build one for the inverse scattering.
Okay. Thank you very much again.